Greetings to everyone. I am Saurabh Chaudhary and today I am here with this video which aims to explain the basic principles behind solving the problems of fluid mechanics assigned to us for our Sessional test 2. So here is the first question. It says consider the velocity field v vector is equal to a within bracket x square minus 6x square y square plus y to the power 4 I cap plus a within bracket 4xy cube minus 4x square y j cap in the xy plane where the value of a is 0.25 per meter cube per second and the coordinates are measured in meters. Is this a possible incompressible flow field? Calculate the acceleration of a fluid particle at point x and y equal to 2, 1. So we have to find the acceleration of the fluid particle at this point. So first we will write the given part. So velocity field of xy plane is given by this v vector is equal to this equation which is given in the question. So the x and y component of the velocity are u is equal to a within bracket x to the power 4 minus 6 x square y square plus y to the power 4, and the value of v is equal to 4xy cube minus 4x cube y, and the value of a is 0.25 per meter cube per second. So let's move on. So the continuity equation for two-dimensional incompressible flow is given by this equation, which is del u by del x plus del v by del y is equal to 0. Now we will put here the values of u and v in this equation. So these are the values of u and this is v, and after doing the differentiation we get del u by del x plus del v by del y is equal to 0. Now since the values of u and v satisfies the continuity equation, therefore the given field is a possible incompressible flow field. Okay, and since there are no time dependent terms, it is steady flow. Yes, as you can see there is no time dependent term here, so it is a steady flow. So there will be no local acceleration in the x and y components of acceleration. Now to find the x component of acceleration, we will write it as ax is equal to u del u by del x plus v del u by del y, and we know since del u by del t is equal to 0, so here also we will put the values of u and v, and then we will differentiate it and we will get this equation ax is equal to a within bracket x square minus 6x square y square plus y to the power 4 into a within bracket 4x cube minus 12xy square plus 4 within bracket 4xy cube minus 4x cube y a into minus 12xy square plus 4y cube. Okay, so now we will put the values of x, y and a, which are for x we will take x equal to 2, y is equal to 1, a is equal to 0.25. so after putting these values in this equation we will get x component of acceleration as 62.5 meter per second square, and in the similar way we will find the y component of acceleration. For this we will take this equation ay is equal to u del v by del x plus v del v by del y. So since del v by del t is equal to 0, so in a similar way we will put the values of u and v here in a similar way. So after doing the differentiation we will get this equation, that is ay is equal to a square within bracket x to the power 4 minus 6x square y square plus y to the power 4 into 4y cube minus 12x square y plus a square within bracket 4xy cube minus 4x cube y into 12xy square minus 4x cube. So in a similar way we will put the values of x, y and a here in this equation, and therefore the y component of acceleration we will get as 31.25 meter per second square. Now to find the acceleration of fluid particle, we will use the formula A is equal to root over ax square plus ay square. So we will put here the values that we have got of ax and ay, then we will square it, and after the calculation we will get a is equal to 69.87 meter per second square. So this is the acceleration of fluid particle at point x comma y is equal to 2 comma 1, which is 69.87 meter per second square. So let us move on, and this is our second question. It says an incompressible liquid with negligible viscosity flows steadily through a horizontal pipe. The pipe diameter linearly varies from 4 inch to 1 inch over a length of 6 feet. Develop an expression for the acceleration of a fluid particle along the pipe center line. And we also have to plot a graph of velocity and acceleration versus position. And the inlet center line velocity is given as 3 feet per second. So here's the diagram. This is the diagram of the pipe. This is the larger inlet whose diameter is 4 inch. This is the smaller outlet whose diameter is 1 inch. And this is the length of the pipe is given as 6 feet. Write this given part first. Length of the pipe, which is L is equal to 6 feet. Diameter of larger end of inlet, which we denote as DI, is equal to 4 inch. Diameter of smaller end of outlet, D naught, is equal to 1 inch. And diameter at any section from a distance x from larger end. So from a distance of x from the larger end, the diameter is given by this formula. D is equal to DI plus D naught minus DI by L into x. Now flow rate is given by, we know the equation of flow rate is Q is equal to AI VI is equal to EV. So in place of AI we will write pi by 4 DI square DI square, which is equal to V into pi by 4 within bracket DI plus D naught minus DI by L in x whole square. So after simplifying this, we will get V is equal to VI by this, and finally we will get this equation for V, which is V is equal to Vx is equal to Vi by 1 plus x into d naught by di minus 1 by L whole square. So now by putting the values of x as 0, L by 2 and L, we will get the values, we will get different values for V. So for x equal to 0, the value of V is 3 feet per second. For x equal to L by 2, the value of V is 7.68 feet per second, and for x equal to L, the value of V is 48 feet per second. Okay. Now the acceleration of fluid particles along the pipe center line is given by this equation Ax equal to V del V by del x. This is the formula, which and now we will put the values of V here like this, and after simplifying this we will get Ax, which is that is acceleration of x, as minus 2 Vi square within bracket d naught by di minus 1 divided by L into 1 plus x within bracket d naught by di minus 1 divided by L whole to the power 5. In a similar way, now we will put the values of x as 0, L by 2 and L, and the acceleration values. You can see for x equal to 0, the acceleration is 2.25 feet per second square. For x equal to L by 2, acceleration is 23.6 feet per second square, and for x equal to L, acceleration is 2.30 into 10 to the power 3 feet per second square. So like this we will solve this problem. And I have shown the graph here. The first graph is the velocity versus position graph. This is velocity, this is position, and this is the curve that we get for the velocity versus position graph. And the second graph is the acceleration and position graph. This is the acceleration, and this on the x-axis is the position, and the y-axis is the acceleration, and this is the curve that we get. So let's move on to the next question. So here is our last question which we will discuss today. It says for a flow in the xy plane, the x component of velocity is given by u is equal to ax within bracket y minus b, where a is equal to 1 per feet per second and b is equal to 6 feet, and x and y are measured in feet. Find a possible y component for steady incompressible flow. Is it also valid for unsteady incompressible flow? Why? How many y components are possible? So first we will write the given part. So x component of velocity is given as u is equal to ax within bracket y minus b, and value of a is 1 per feet per second and value of b is equal to 6 feet. For two-dimensional incompressible flow, the continuity equation, which we know that it is given by del u by del x plus del v by del y is equal to 0. So we will put del u by del x to the other side, so del v by del y is equal to minus del u by del x, and then we will put the values of u here. Del v by del y is equal to minus a within bracket y minus b. So we will get dv is equal to a within bracket b minus y dy, and let us mark it as equation 1. So now we will integrate this equation 1 which we have marked to both sides. We will integrate it both sides, then we will get the value, the equation of v as v is equal to a within bracket b y minus y square by 2 plus f of x comma t. So here this f of x comma t is an arbitrary function of its argument, and since it is a steady flow, there are no time dependent terms, then f of x comma t is equal to f of x is purely dependent on x. Now we know that it is a steady flow, so there should not be any time dependent terms. So this f of x comma t we will take as f of x. It is equal to f of x. So now since f of x is arbitrary, there are infinitely many possible y components of velocity. So in the question it was asked how many y components are possible. So we have found that infinitely many y components of velocity are possible, and after making this f of x comma t is equal to f of x, we will get this equation v is equal to a within bracket by minus y square by 2 plus f of x. Now the possible and simplest y component is when f of x is equal to 0. So this f of x, its value is equal to 0. So the simplest y component we will get as v is equal to a within bracket by minus y square by 2. So therefore it is not valid for unsteady incompressible flow, because for the flow to be unsteady it should have a time dependent term which is not there. Now in the question it was also asked that is it valid for unsteady incompressible flow or not. So it is not. So we found out that it is not valid for unsteady incompressible flow. The reason is because it should have a time dependent term to become unsteady, but it is not present. This time dependent term is not present, so it is not valid for unsteady incompressible flow. So let's move on. Now the two velocity components which we get are u is equal to ax y minus b, and v which we get v is equal to a within bracket by minus y square by 2. Okay, now as this value of a and b were given in the question. So putting these values of a and b in the above equation, we will get value of u as x within bracket y minus 6 bracket close feet per second. U is equal to x, y minus 6 feet per second, and value of v is equal to 6y minus y square by 2 feet per second. Now, however, if it would have been an unsteady incompressible flow, suppose as in this for this question it is not valid, but if suppose it would have been a steady incompressible flow, then the velocity components will be u is equal to x within bracket y minus 6 and v is equal to 6y minus y square by 2 plus f of t, and this f of t is an arbitrary function of time, and due to this it would have been an unsteady incompressible flow. But since this term f of t, the time dependent term, is not present, so this question is not valid for unsteady incompressible flow. Okay, so hope you like this video. Thank you.